Welcome back. In this video we continue our development of a mathematical model for uniform circular motion. In this diagram we're depicting the motion of a particle traveling around in a circle with uniform circular motion. So at some point in time the particle is here, and then some time later the particle is at this point. So here the particle has some initial velocity and here it has some final velocity. This vector, the velocity of this particle, is tangent to the circle at all times. That means it's going to be perpendicular to a line drawn from the center. In other words, the velocity is always perpendicular to the radius. Since it's uniform circular motion, the magnitudes of these vectors are equal. So that's what we have here. And we'll say then that the magnitude of this velocity is simply v. So as this particle travels, it sweeps out an arc, which we call delta theta. So this is the angular displacement. Of course, it travels a distance s, which is the length of this arc, and we know that the angle in radians is defined. So this angular displacement is going to be defined as the ratio of the length of this arc to this radius. Now let's divide both sides of this equation by the time interval, and we write it this way. So it's s over delta t, and of course this can be written as 1 over r. But we know that delta theta over t is the angular speed, and s over delta t is simply, you know this from a long time ago, that's just basically distance divided by time. So that gives us the speed, and so we can simply then multiply both sides by r, and that gives us then that v is equal to omega r. So this is a very important relationship that you need to know. You're going to see this pop up a lot. So the linear speed of a particle moving with uniform circular motion is equal to the product of its angular speed and the radius of the circle. So make sure you understand this development here. We now look at the acceleration of a particle moving with uniform circular motion. As this particle moves around in the circle with uniform circular motion, its speed is constant. However, since the direction in which it is traveling at each point in time does change, for example at this point in time its direction of travel is as indicated here. When the particle is here, its direction of travel is different. Therefore, even though the speed of the particle remains constant, its velocity changes. Remember, velocity is a vector, therefore since all vectors have both a magnitude and a direction, change any of these and you have changed the vector. So here what's changing is not the magnitude of the vector, but its direction. Therefore, the velocity changes. If the velocity is changing, the particle then must be accelerating. Acceleration, if you remember, is the rate at which velocity changes. So if velocity is changing, the particle must be accelerating. So what we want to do here now is get an expression for the magnitude of this acceleration. To do this, we will divide the magnitude of the change in the velocity by the time interval. Note I said the magnitude of the change in the velocity, not the change in the magnitude. There is no change in the magnitude. The change in the magnitude of the velocity would be 0 because the speed is constant. What we want to do is find the magnitude of the change. So now to do this, we simply need to take the velocity at 2 instants in time and subtract them. So here we have the velocity at some initial point in time and the velocity at some later point in time, and we're going to call this the final velocity. And so we draw the two vectors tail to tail, and this vector then is the change in the velocity, and what we want then is the magnitude of this change. If you recall, an angle in radians is defined as the ratio of the corresponding arc to the radius of the circle. So you may not see it here, but we can look at these two lines as the radii of a circle. So maybe with this circle drawn here you can see what I'm talking about. Now this circle is not this one. I'm just drawing this here so you can see that we can look at these two vectors here as radii of a circle. This angle then can be defined as the ratio of the length of this arc to the length of this vector here. Now we are not really interested in the length of this arc, we're interested in the length of this vector. But notice that as this angle is made very small, so let's suppose we're doing this analysis now for a very small angular displacement, infinitesimally small, 0.000 to infinity, 0.0000001. Imagine an infinite number of zeros there. So this angle is very small, but not 0. In that case then, the ratio of the length of this arc to the length of this vector would be 1. In other words, the length of this arc would be equal to the length of this vector if this angle were infinitesimally small. And so then we're going to define this angle then as the ratio of the length of this vector to the length of this one. Right? So that's what's happening here. So we have that this angle is the ratio of the magnitude of the change in the velocity to the magnitude of the velocity at any one of these instances in time. So very simple algebra here, and so we have the product of the speed. Remember, the magnitude of these velocities is simply the speed, which is constant. So we have that the product of the speed and the angular displacement is equal to the magnitude of the change in the velocity. Note, it's the magnitude of the change in the velocity, not the change in the magnitude of the velocity. Dividing both sides by the time interval, we get this expression here. The angular displacement divided by time is the angular speed, and of course the magnitude of the change in the velocity divided by the time is the magnitude of the acceleration. So this is what we wanted to find. This is a very important relationship. Make sure you know this. The magnitude of the acceleration of a particle traveling with uniform circular motion is equal to the product of the linear speed and the angular speed. So make sure you know this. Okay, so we know that the magnitude of the acceleration of a particle undergoing uniform circular motion is equal to the product of the linear speed and the angular speed. We can use this expression here that we developed not too long ago to find alternative expressions for the magnitude of the acceleration. If we substitute for v here, this then becomes omega squared r, and if we substitute for omega, note omega is v over r, so the magnitude of the acceleration then becomes v squared over r. So these two expressions in fact are the more popular. So when solving problems, students normally use this one or this one. So that's it for the magnitude of the acceleration. Now how about the direction? Remember, acceleration is a vector, and so far we have only found an expression for the magnitude of that acceleration. Now we need to make sure we understand just what the direction of that acceleration will be. Let's take a look at these diagrams again. Here we have the initial velocity, the final velocity, and we set them up like this to find the change in the velocity, which is this vector here. As this angular displacement approaches 0 for infinitesimally small values of this angular displacement, to what value does this angle here tend? So the question is, for very, very small angles here, what value would this angle have? So let's take a closer look at this. It should be pretty obvious, but maybe it's not. So here we have the initial velocity, the final velocity, and the change in the velocity. And we want to know, well, as this angle becomes very small, what value does this angle approach? So notice this angle right here. So let's make this angle a little bit smaller. Notice it's smaller. Notice this angle here. Let's make it a little bit smaller. Notice what's this value approaching. Same thing goes over here. So these angles are equal. This is an isosceles triangle, if you hadn't noticed, right? These sides are equal. The initial velocity and final velocity have the same magnitude. And so let's make this angle a little bit smaller. No, I can't make this infinitesimally small. So here it's smaller yet. What is this angle approaching? Let's make it a little bit smaller. So what value is this approaching? So imagine this were extremely small, 0.000000, an infinite number of zeros, then 1. What value would this be? If you said 90 degrees, then you would be correct. So that means the change in the velocity would be at 90 degrees to the velocity of the particle at all times. So what is the direction at 90 degrees to these velocities? Well, that would be, in this case, the change in the velocity would be pointing like that here, and here the change in the velocity would be pointing like that. So notice the change in the velocity is always pointing towards the center of the circle. Now if you remember, acceleration is a vector that points in the same direction as the change in the velocity. So that means this particle, as it goes around in a circle, is accelerating towards the center of the circle. So the acceleration is always at 90 degrees to the velocity, which means then that the acceleration will not result in a change in the speed or the magnitude of that velocity. It will only manifest itself as a change in the direction of that velocity. So that's what we have here in this diagram. The acceleration at all times is at 90 degrees to the velocity and pointing towards the center of the circle. So because it points towards the center of the circle, we say that this acceleration is centripetal, not centrifugal. Not centrifugal. Do not call this acceleration centrifugal acceleration. The acceleration is centripetal. Of course, if the particle is accelerating always towards the center of the circle, then there must be some force making it accelerate towards the center of the circle. And that force we will call the centripetal force. Now remember, there is no special acceleration or special force which is a centripetal force. Any force that's making this thing go around in a circle, in that particular case, that force would be the centripetal force. So we saw examples of this in the past. So if somebody is on a skateboard and they're going around a loop, well, the very surface is providing a normal force that's pushing the person around in that circle. And so that normal force in that case would be the centripetal force. Or the tension in a rope, if you're using the rope to spin something around, the tension in that rope would provide the centripetal force. In this diagram we see the net force depicted. So note the net force is always in the direction of the acceleration. And so in this case, since the acceleration is centripetal, the net force is also centripetal. Both the net force and the acceleration are at right angles to the velocity at every point in time. So again, remember, there's no special force out there called the centripetal force. Any force that is responsible for making something go around in a circle, well, in such a situation, is acting as a centripetal force. Centripetal simply means some force that is acting to the center of a circle. So in this case, the applied force, this component, provides a centripetal force. Here, the net force acting in this direction is made up of the weight and the normal force. Here, as this car passes this point here, we have that the net force is the sum of these forces. So next we look at some problems and see how we can apply all of this to their solution. So that's it for now.